Hello and welcome to this edition of selection rule presentation on the EPR spectroscopy. So far we have seen the selection rules for NMR spectroscopy, UV visible spectroscopy, INR spectroscopy. This has been very useful in deducing the spectral interpretation. If any spectra is given, it becomes very essential to know the selection rules we have seen. In the case of EPR spectroscopy, the individual electron spin is considered for the spectroscopic techniques, while in NMR we use the neutron magnetic moment. The main difference between them is in the NMR spectroscopy we use magnetic field as static one and then pass on the radio frequency which fills the nucleus. Then we measure the relaxation time, we get the peak. But in the case of IPR spectroscopy, we use microwave radiation which is held constant and the magnetic field is varied. So you get a relaxation time and the electron gets excited and then the peaks are then accounted for. That means the magnetic field has to be varied, but the microwave frequency is kept static. The reason is the sensitivity of EPR spectroscopy is very high because it is dealing with the electronic orbital momentum and the electronic magnetic field, its interaction. We have very few systems that interact with the magnetic field, particularly the free radicals. However, the alignment is quite similar to what we have seen in NMR spectroscopy, where one proton is aligned with the field and the other proton is aligned against the field. The same thing is happening here in this case also. The equation that GBMS, that is the gyroscopic constant, magnetic field strength and the spin, electron spin's magnetic moment, gives rise to the momentum. That should be kept in mind. So before turning to the EPR spectroscopy, which we also call it as the ENDOR or ELDOR, some few techniques are there, double resonance techniques, single resonance techniques. But it is essential that we classify some molecules which actually possess the magnetic moment due to the electron.
Okay, here it is. So you can see the EPR as well as ESR spectroscopy. Electron paramagnetic and electron spin both are same, and you can see this NMR type precision being done here. Electron paramagnetic resonance, often called spin resonance, is a branch of spectroscopy in which electromagnetic radiations, usually in microwave frequency, is absorbed by the molecules having electrons with unpaired spins. And let us see the selection rule also here in this presentation. While the NMR technique deals with the non-zero nuclear spin, the ESR deals with the electron paired spin. So here is a comparison. EPR focuses on interactions between an external magnetic field and unpaired electron. This is important here, whatever system it is localized to. The electromagnetic radiation used in NMR is radio frequency only, which is falling in the region 300 to 1000 MHz, whereas EPR is typically performed in the microwaves region 3 to 400 GHz. So both have the magnetic field and the radiation frequency only varies. In the first case, NMR, you have radio frequency. In the second case, you have microwave frequency. In EPR, the frequency is typically held constant, so it is not varied, while the magnetic field is varied there. So you can see that. This is the reverse of how NMR experiments are performed, where magnetic field is held constant and the radio frequency is varied. So the relaxation time, which decides the shape of the peak can also be comparable. In EPR experiment, must be performed at a very low temperature because they are very sensitive and often below 10K and sometimes as low as 2Q. This typically requires use of liquid helium as a coolant. And it is roughly 1000 times more sensitive than NMR spectroscopy due to higher frequency of electromagnetic radiation. In principle, EPR spectra can be generated by varying the photon frequency incident on a sample while holding the magnetic field constant or doing the reverse. But often reverse is done and radio frequency, the microwave frequency is varied. By varying the external magnetic field, microwave frequency is kept constant. By varying the external magnetic field, the gap between the upward and the downward spin energy is widened until it matches the energy of the microwaves. So that which we say as the field in transition metals, we have got the delta E value, crystal field splitting. Same thing is there, but that is in the visible region and this one is in the microwave region. So you can have a comparison between them. And unpaired electrons move between two spin states. So this happens to be the initial thing about the selection rule. I again stress that the selection rule is something which can always tell you what type of peaks you will get, whether they are split, whether they are broad, whether they are vague, whether they have a very good area under them, or whether they are sharp. So it's a universal factor that can let you interpret any spectra that is given to you. So let us start with the ground state where S is equal to half. So this I'll tell you about this doublet later, and this is the S equal to half of the hydrogen atom having single electron, hence L equal to 0, and S is equal to half, J is equal to half. J is the orbital moment number. Under the magnetic field, this level is split into two energy levels, one aligned, one against, and they are represented by magnetic momentum, the spin as plus half and minus half because ML is equal to 0. Azimuthal quantum number. The splitting energy due to the magnetic field is given by this formula. We need to remember this formula as a universal formula, G mu B. We will see later in the coming slides what G stands for and what mu and B stands for. As is shown here is the field there. The transition between this level is governed by the magnetic dipole selection rule. Here it is, that selection rule, which says that delta L should be equal to 0 and delta S should be plus or minus 1. You can recall the selection rule with the UV visible spectroscopy and the NMR. In the NMR also it is the same thing as delta S. MS for the proton is equal to an odd number. Transition changes the spin projection here by plus or minus 1. So you can see that this is in fact this is the ground state. You can consider this as a ground state when you want to compare it with the UV visible spectroscopy. Then you have an applied magnetic field. In the applied magnetic field, you get a splitting of 2 mu B and Bz, and they are separated by this energy which is in the microwave region, H nu. That's how you get it. The region you go to Bz. You represent one by half and another by minus half, which is downfield, and then you have the absorption because of that, a peak that is going like this. Sometimes a derivative is I think you can study separately how derivative peaks are useful. They in fact summarize the change in the pattern with change in the field. While this is a direct representation, sometimes it is not useful. In the derivative, you get a change with respect to time, with respect to energy, some very simplified thing. Since we have 2Bz equal to, that is the magnetic field applied, as equal to this, you can see that Gj is equal to Gs because L equal to 0. So H nu, which is G mu B, H mu, in fact you can even write it like this, G mu B equal to 2 mu B. The applied field, you can just bring this downwards there for frequency, and then 2 mu B H. You can substitute this and you will get the 2.8 megahertz per Gauss. This is the outcome of the selection rule calculation. So it can be seen that the frequency required for transition is about 2.8 megahertz per Gauss of the field applied. So you can compare this with the magnetic field of the Earth, which is about 3 to 4 Gauss. The entire Earth has a magnetic field, and this is therefore very sensitive. So you can see how it is 2.8 is very closer to the, in fact the Earth's magnetic field is higher than this particular flipping. This means that for higher magnetic field is employed in the laboratory, the radiation request belongs to the microwave region. When the magnetic field used is about 3400 Gauss, the corresponding applied frequency required in the magnetic field spectrum is close to 9 to 10 gigahertz. This corresponds to a wavelength of 3.4 centimeter, known as the X band. It's the name we give for the same. In both EPR and NMR, the sample material is immersed in a strong magnetic field and exposed to an orthogonal low amplitude. It's quite right angles, amplitude high frequency. ESR usually requires microwave frequency. NMR is observed in the low radio frequency. This need not be forgotten. With ESR, energy is absorbed by the sample when the frequency of the radiation and the energy difference between the two states of the electrons is sample, but only if the transition satisfied the appropriate solution. So transition, it doesn't usually take place for paired electrons, therefore you get electron and paired electron. And pairing usually results in zero electronic spin, thus EPR is silent, but some can provide an EPR signal. They can be classified into three groups. Let us look into them. First one is the transition metal and rare earth species which contain unpaired d electron or F electrons. The experiment will examine liquid solution in Mn2+, F3+, and Cu2+ with some ligands as well as chromium ligand and dilute in solid aluminum trioxide as a solid sample. The second one is a small number of organic molecules are called free radicals because they contain a single unpaired electron. DPPH and TEMPO are some most common use examples. The latter will be used in the first part of this experiment. I am not including this, but just mentioning it here. All but one of the electrons of these molecules are paired. So there is only the orbital and spin motion of an electron present per molecule. Per molecule, per spin, and per orbit. Then the third one is the organic ion radicals, very reactive species which are created along a course of redox reactions. They can be stabilized at certain conditions, usually temperature. You will make this Berlin, give an example at the end, cation radical and benzoic ion radical. Absolute requirement is some stable species like this. Transitions like this. Lifetime is 10 nanoseconds and it can detect 10 power 11 spins easily. So this you can compare with the resonance, use ordinary resonance in the organic molecules which are about 10 power 6 times per second. So it's quite very fast. Now the MCW region of the spectrum, calcium, and that is the cited as 9.5 GHz. Magnetic field rate as 0.533 Tesla. The energy of the electron is given by equal to half GB mu B, GB mu, where mu B is the Bohr magneton. So we need to remember this value as a joules per Tesla, 9.274. Mu B is defined by EH by 4 pi m. G is a dimension, and this G value is what we see as chemical shift. Here in NMR we see it as delta. We should know the G value. So in the coming slides I am going to tell about this. For electron, the spin quantum number is s equal to half with components ms equal to plus half. So you have two components there. Thus, an unpaired electron whose spin orientation is opposite to that of the applied magnetic field has a lower energy, it's minus half, and plus half for the high energy. The nucleus is so here is the representation of field on plus half, higher energy, lower half. So we have already seen this. Now the resonance equation, how just they resonate unless you reduce the frequency. This value Bohr magneton we need to remember, and here you can see the simple setup of the experiment, the detector and the source. Here is the magnetic field, so it is equated like this. So you can see the alpha state and the beta state. Beta state is a lower state. Because of interaction of the unpaired electron spin given by two projections ms plus and ms of electron with magnetic field, the so-called Zeeman effect takes place. So where this effect is take place, you need some interactive magnetic field, which is given by SI units in Tesla, and it is about 0.0001 T. Some units we need to remember by heart. Other terms given in the previous equation, ms is the spin obstruction in the field, ms equal to plus or minus half for a free electron, and mu b is the Bohr magneton. So here is the so you need to remember this, where E and M are being electron charge and mass ratio. Here it's Planck's constant. Parameter G is often obtained in this EPR spectroscopy. As a value, we call it as the constant, which is often 2.003. Up to this we stop, and this is called as G value. You need not forget this, and it is sometimes called as Landis splitting factor. So G equal is given by 1 plus S into S minus S plus 1 minus L into L plus 1 and J. So it is a calculated finance. The overall magnetic moment BFS can be expressed by angular momentum and G value. For most free radicals, the unpaired electrons have L close to 0 and the total electron quantum energy is pretty much the spin quantum number. As a result, their G values are close to 2. Situation becomes much more complicated with the transition metals. Not only these have large L's and S, but these values depend on the surrounding electric fields of ligands, making everything messier. If the molecule contains nuclei with magnetic moments such as protons, okay, this is a new consideration. The interaction with external field and the electromagnetic field will change the stationary energies according to this. And I am skipping this because it will make things more complicated and we will require extra time to go into that. But have a look at this, where we just generate an equation electron nuclear interaction as given by A, ML and MS for obtaining the hyperfine coupling. So the idea is to find out what hyperfine coupling is. It's a coupling of this proton with coupling of an electron with the magnetic moment of the proton. Sometimes they may be matching, so it is represented by that. So you get a hyperfine splitting. There's like these regions. This is given by that equation 10. I should know two important things. Signs in front of the G and Gn are different because of the opposite charges of the electron and the proton. Electron and proton, causing the spin of the electron to be higher and spin of the proton to be higher energy than An. Magnetic field of the electron differs from B0 by integer times Aj. So this is the equational definition, but we can remember the Landis splitting factor can be two types. Compute the G value for ALS3. It is sometimes as G equal to H nu, this frequency MB by N. So the values are given. You can simply substitute. Here you can get this is a reference. So a simple substitution can give you the G value. Sometimes G value is given. You're asked to calculate nu. G value is slightly changing. Like for example, 2.0025. It should be 2.3. It should be 2.4 or something like that. And the standard, well-known standard that use for comparison is Mn2 plus, which has got a I equal to 5 by 2 doped into MgO at a high dilution. Separation of 2 Mn2 plus line is taking place at 8.69 Tesla. Therefore, An equal to, in the previous formula equation number 10, 1.3 Mt, and the G equal to 2.0027. So a splitting, you can see 1, 3 and 1:3. Hyperfin coupling is given by this formula, so you can take down this, because if I start explaining it will take a lot of time. My purpose was here to suggest the selection rule, what type of electrons will answer the EPR, compare it with NMR. So you can easily exclude out which molecules do not answer the ESR spectroscopy. And about the intensities of the lines, some are given there. You can make a note of this. The VO2 plus has got 8 lines. So these are the lines 1, 2, 3, 4, 5, 6, 7. Typical ESR spectrum goes like this. Hydrogen atom has 2 lines. Hyperfin coupling is at 50.7. Splitting between these two is microtesla. Independent of the material. G value measured in the center of the multiplate. Note signal presented as derivative of ds by dB, spin by magnetic field. So the Zeeman effect is the degenerate energy levels, and that is at about 10 gigahertz. And nuclear Zeeman splitting at the, you can see that this is a zero field and split in the magnetic field by the neutron there. Okay, so they interact and get lot of these settings, plus half, minus half, plus half, minus half. This is nu 1 and this is nu 2. Okay, so that is given by these two things. So the origin is dipole-dipole interaction, electron and nucleus. Origin is dipole-dipole interaction, electron and nucleus. If the electron in s orbital or molecule rotates rapidly, as in a gas phase solution, then dipole fold averages its to 0, non-zero solid state, anisotropic coupling. And then Fermi contact interaction is also possible depending on the electron density of the nucleus. The calculated values are given. For this, you have to look into the Fermi resonance, and that can be explained by molecular free orbital theory. That you can see that an electron in 2p evapolarizes sigma electrons, so that the neighboring electron has the same spin. Okay, the other electron has an opposite spin. Near the H atom, one bond, one is atomic orbital, so electron can interact with the magnetic nucleus. So that means, a 2p unhybridized electron can polarize the electron in the atomic orbitals. Then that can be sensed by the ESR spectroscopy. That is a very good advantage of having the ESR. Same thing is with the allyl radicals. So you get a lot of shapes like that. And then you have the spin labels, how to represent them. If all your ESR spectra should have that spin labels like that. So here also you can mention like this. Okay. So with this I stop the presentation.